What a wonderful day, my friends. I try to keep the world partial really not upside down. I try my best. So soon we will start our wide band gap uh, session. I see all the authors are on stage. I just give the introduction today. Alfred Vollmer will monitor the sessions. And yeah, what can I say? I hope still in this world the law of Ohm is still valid. Sometimes, if I read the newspapers, I'm struggling in understanding what's truth and what's fake. So, economic situation from the past had shown that the world is operating like a gearbox. And if you damage the wheels, the teeth wheels, or put too much sand into it, it will collapse and did not work proper anymore. I hope we will overcome that situation and get back to a normal trade and honest behavior between partners. So, Alfred, take your part.
Okay, I'll start right away. Welcome, everybody. Some of you may already know me. I'm editor-in-chief of Bodo's Power Systems. And I would now like to welcome Paul Drexhage, who will tell us something about the 2 kilovolt SiC power modules, which transform 1500 volt systems. He will discuss his story more in detail, and I would like to hand over to not Paul, but I think no, Paul is here. Okay, I saw him. So, Paul, the stage is yours. Please go ahead.
Oh, thank you. Excuse me, my voice. Thank you very much, Alfred. I'd also like to welcome my colleague Stefan Häuser here, who will assist me as my voice has been a little bit damaged here. But yes, we have Semikron Danfoss has a large silicon carbide portfolio, and as one of the leading chip-independent power module manufacturers, we've expanded that portfolio with 2,000 volt ROHM devices here that we think will make a large difference, particularly in the areas of renewables and energy storage systems. Feel that there is a trend towards higher DC link voltages across various industries. And although these applications are well served by 3-level converters in silicon, there's a lot of advantages in terms of simplicity, system size, and even efficiency with moving these systems from 3-level voltage source silicon converters to 2-level silicon carbide converters.
Okay, I think we have got some questions, and probably our team can put the questions on the screen so that we will be able to read them. Did something arrive already? Yeah.
Perfect.
What silicon carbide products does Silicon Danfoss offer? You already gave a slight introduction. Probably it is worth to say a few words on top of that.
Well, we are a power module manufacturer, so we have a variety of power semiconductor modules in industry standard packages. And for the 2 kV silicon carbide product line in particular, we start in our lower power with what we call our semi-top E package. This is a PCB mount device, and then move up in the medium power range to the classic 62 millimeter module, our Semi-Trans 3. And then for higher power applications, we have adopted the industry standard derived originally from the traction industry, our Semi-Trans 20 package. And this moves us up into the megawatt range. As an organization, Semikron Danfoss is also able to offer additional value add to that. So we have intelligent power modules. Our classic SCIP module that's been very popular in the wind industry is now available with 2 kV silicon carbide chips. And that silicon carbide SCIP can also be integrated into some stacks, some larger power converter assemblies in a nice form factor that goes into like a Rittal cabinet, for example, to make it very easy to get to megawatt class converters in a very short time.
Okay, thank you. So before we start talking about the technical questions, I would like to encourage you to really write your questions into the chat in order to enable us to have more questions that need to be answered. But here's the first technical question. Why should we use 2 kilowatt silicon carbide when there is already an established silicon solution with 3 level?
The simple statements are simplicity. That would be from a 3-level converter down to a 2-level converter. Size reduction, and that would be physical size reduction of the entire converter. And believe it or not, efficiency. So the beautiful thing about the 2 kV silicon carbide is we can reduce the size of a power converter. And I talk a little bit about that in my article with a 1 megawatt example of this 2/3 size reduction. We can reduce the physical size of the power converter and still achieve an increase in efficiency. So obviously those 2 points on their own are very attractive. The more obvious stuff comes from moving from a 3-level topology to a 2-level topology. Obviously, with a 3-level for a single phase leg in 3-level, we obviously need multiple driver channels, depending on whether you're an NPC or an ANPC topology. And with a 2-level converter, we can move back to a simple 2-channel driver for each phase leg. And so there's some cost and complexity savings there. Certainly in the control algorithms. For example, these 3-level converters usually require a voltage balancing algorithm to make sure that the voltage is balanced across the DC link, and that control loop can be a bit tricky to implement. So yeah, there's savings on multiple fronts here from a size, efficiency, and simplicity.
Okay. Before we will go to the next question, I want to outline that we will have 3 different companies and 3 different speakers in this session, all talking about SiC. And I will introduce these speakers later. So now this is the Semikron Danfoss or Danfoss. How do you pronounce it, by the way? Danfoss or Danfoss?
I'll let the guy without the hoarse voice say it clearly for you here.
That is honestly up to you. As a German, we usually say Danfoss, right? But the moment you switch to English language, it's Semikron Danfoss.
Okay, let's say Semikron Danfoss. Semikron Danfoss, sorry. And the question to you is, why a blocking voltage of 2 kilovolts and not 2.3 kilovolts?
Yeah, so there's a number of devices on the market now from our I'll say competitors, but our other people in this industry. When we have chosen for our primary product here, although we're chip independent and we can source chips from a variety of manufacturers, our primary product is a Rohm 2 kV device, and other silicon carbide manufacturers are looking at 2.3 kV or 2300 volt devices. For us, with the Rohm chipset, we find that it's very well behaved and doesn't need any additional voltage margin to deal with voltage spikes that you might see during switching. Okay, over voltage spikes with silicon carbide are particularly of concern due to the fast switching transients, and this can be amplified by poor module design, high stray inductance within the power module. And then I guess the other point that many people worry about is cosmic ray failures, these cosmic ray fit rate failures in time. And again, speaking for our product and our personal device, we find that the 2 kV Rohm chip is excellent in regards to this. And we can tell you that some major solar inverter manufacturers are comfortable with this chip technology as well. So for us, that's why we've chosen the 2 kV.
Okay, so another question. Motor drives are a commodity market. So why would motor drives manufacturers want to use SiC in their drives if this is way more expensive than silicon IGBTs?
Okay, so this is from our article about silicon carbide in motor drives, and now we're speaking about general silicon carbide, but more specifically 1200 volt devices. And so for that, I will hand it off to my colleague Stefan.
Yeah, thanks, Paul. Yeah, that's an interesting question, actually. Yes, silicon carbide is more expensive, and I think everybody who looked into silicon carbide has experienced that. But this is always the case if you compare it really on the die level, on the discrete level, on the module level. But if you look into the complete system, and that's obviously the most important part here, if you look into the complete system, silicon carbide comes with a lot of benefits that actually also Paul already mentioned, right? You can go from a 3-level solution to a 2-level solution in the renewables, and you have a different set of advantages on motor drives. So let's maybe look at the two parts on motor drives, the AC to DC on the input side, where usually you have a 6-port rectifier, or if you need an active front end, it's an IGBT. So you're somehow limited in switching and limited in performance here. If you go to silicon carbide, you're basically at the same situation as you would be at renewables. You have a way more efficient device, means lower losses. Lower losses means you need lower cooling effort. You run at higher efficiency. You can push the switching frequency quite a bit, and with this save on magnetics. And then we save on magnetics, they usually become smaller. So the overall size of the system will be also reduced. And that has other implications: reduced space in the cabinet, reduced weight for shipping. That's the active front end side. But of course, the majority of drives still has just a passive rectification, as I said. So on the output side, on the inverter side, it's a bit more tricky, because here you can just not utilize the higher switching speed. You have to look for other advantages. And we found that especially with quadratic torque drives, so everything that's driving a fan, a pump, or even a heat pump, here we have the situation that the drives are never running full speed and full torque, full power, but they are running in a kind of a, let's say, 40 to 80% range of power. And here the MOSFET comes with benefits, because it has the linear voltage drop and not the bend curve that we know from IGBTs. And that leads to significantly lower losses on the forward voltage drop side as well. And that helps you, of course. So you're running in the partial load area way more efficient, and you do not have to switch fast to take the full advantage of the silicon carbide. Side note, why do you not switch fast on a motor drive? Because you usually have a limitation on switching speed of the motor itself. So something like 5 kV per microsecond is usually the maximum that these motors can do. Maybe once in a while you find one with 10 kV, but you would like to limit that. And still you save on the efficiency. And if you increase the efficiency, you lower the losses, then you have the same as before. You have a set of advantages that you can utilize. You drive higher currents. You go with a smaller drive because you might reduce the heatsink, less cooling effort, or you might reduce the current rating of the device. Overall, you're using less energy, and that also helps to improve the CO2 footprint. But now the real question is, we talk about money in the end. SiC is expensive, so how can it make sense? Through these saved energy that you will not dissipate in an IGBT device, but you just need less to drive the motor. This will help you, and we did some calculations on that. If you take as a reference the German electricity cost today in industry, for a simple pump fan drive, you pay more for the drive if it's silicon carbide based, but you will have a payback of this additional cost within a year just by the energy that you save. And I think a year payback is not bad, because after that 1 year, you save money.
Okay, within a year, that is really an impressive number. So I think SiC will be marching even further forward, because the total cost of ownership is a very, very important issue.
Absolutely. Yeah, I would agree on that.
So I think we are ready for the next question. Have you mentioned a skip module with SiC? You have mentioned a skip module with SiC. Skip are the names of your modules. Is it a complete solution with driver and heatsink? And are there any further features?
Sure. The SCIP, and the SCIP is an acronym for Semikron Integrated Intelligent Power. This has been a flagship product of ours for many, many years, and it includes the heatsink, whether it's air or liquid cooled, the semiconductors, and in this case we have the silicon carbide 2 kV devices. And then a driver circuit, an isolated driver circuit with galvanic isolation. So you only need to connect your controller to the primary side. And so that isolated gate driver, I mean, we've worked on this for many, many years and have developed a lot of features into that. To name a few, there's isolated current sensing, voltage sensing, short circuit protection. Now that's always that's one of the big concerns with silicon carbide, right, is that it has either no or very little short circuit withstand time. So for even the best silicon carbide devices today, we're looking at around 2 microseconds of short circuit withstand time. With the SCIP product, we're able to tailor the driver to be able to turn off the device within that time and hopefully save that device in the event of a short circuit. And then, of course, on the primary side, we have a lot of other features that face the customer, like interlock time and dead time and things like that. So it's really a full-featured solution. It's in mass production for us, so we can be very competitive with that. And we don't want people to think of this as just a solution for prototyping. These SCIP power modules have powered many of the world's wind turbines in the past, and we feel that there's a lot of sense to putting silicon carbide in there, because we can overcome a lot of the design-in issues, supply issues, and variations between silicon carbide chips, right? The different manufacturers have different gate voltages, and this can be very difficult for some users to manage from a supply chain standpoint if they have to have a different driver type for every silicon carbide chip they bring in. So the SCIP manages that and manages it cost effectively.
Good. So now we are going to dig a little bit deeper. The next question is about the EMC problem and about the distortions. And maybe we can put it on the screen. What about the EMC THD advantages of multi-level topologies versus two-level topologies?
So I'll comment briefly, and then Stefan, please step in. But certainly the three-level topology has advantages with regards to the effective ripple frequency. So if we're talking about harmonics on the AC side, you get the natural benefit of having nearly twice the effective ripple at the AC output as your switching frequency. And in addition to that, you're afforded some additional levels of control when it comes to common mode voltage in the system. So in order to deal with that, when you're switching back to a two-level, you need to switch faster. But the beauty of the silicon carbide is we can switch twice as fast as the silicon. So it's possible to implement this two-level solution and maintain the same effective ripple on the output with the silicon carbide.
Okay, thank you. And the last question we have received so far. After that, everybody here who is in the audience will also have the possibility to ask a question directly. With the latest AI server power density requirements, do you see SiC becoming a preferred solution for that application?
I'm going to take that one. This is a bit of a stretch to comment, to be honest, because this is not necessarily our market on the AI server today. And that's exactly the point, right? Power density indeed is increasing a lot. If you look into AI, that's I don't know, I think something like 10 times. And if you look in the past, what you had on a conventional data center up to what might be coming up from NVIDIA in the next 2 or 3 years. Today, it is a discrete-driven business, I believe. And this discrete business is not ours, but power module is. So the higher the power rating get, the more attractive it becomes to switch from a discrete TO device, TO2/7, to a power module, right? And then I would say absolutely yes. We talk about a DC-DC converter here mainly, or flyback converter, and then silicon carbide is definitely a very preferred solution and a very efficient solution. And we see that also in the world of data centers that we supply uninterruptible power supplies, for example. We see definitely a trend to silicon carbide because the efficiency counts. Also, power density counts there as well, because the same size data center suddenly will have a much, much higher connection power. And you see that trend, yes.
Okay. Thank you so much. So, is there anybody who is directly participating and who has his or her camera switched on, who would like to ask a question? The mic is open. Well, if there are no more questions to Semikron Danfoss, I'd like to say thank you so much for your participation. Thank you for answering all the questions of our readers, and hopefully see you at PCIM at the latest.
Definitely. Thank you very much for having us.
Yeah. Thank you for being here at Bodo's Power Systems. So now I already saw Pradip Chatterjee from Nexperia, who got ready. Pradip.
Hi there.
Hi.
How are you, man? Good.
I'm feeling very good. Thank you. How are you?
Yes, going good here. Market is dynamic
You name it.
for everyone,
Yeah,
but
yeah.
there are still chances everywhere.
Of course, and we have to get these chances and we have to make the best out of it.
Exactly, as you said.
That's
So
it.
thank you for having me in this interesting call. I listened to our guys from Semikron, very interesting insights, but we are serving slightly maybe different area than them. So I hope I'll make this discussion interesting.
Of course. So probably we should start already with the first question that came in.
Yes, very good.
Yeah, that was for you. Sorry, I mixed it up.
No, definitely. So AI server is one of the, I would say, most happening industrial application for silicon carbide now. Major focus on the power density, and they have a fixed, I would say, modularity, reliability, and efficiency. These are the three categories. So most of the time, the efficiency is going towards 80 plus titanium now, no? Not even platinum, which says that at 50% of the load, you need to achieve more than 96% efficiency. At 100%, no, 91, 92. So the efficiency throughout the changing load, major challenges for any power application, and this is what AI server needs to achieve. The second is power density. It's going from, I think, 120 watt per inch already done, and it's driving towards 150 watt per inch cube. No, really high. No, so this is the power density. This is called common redundant power supply dimension. No, this is a particular form factor in 1U height. No, and you have to have the stacks basically built upon this building block size. So very challenging, and the power. So power, it started with 7 kilowatt stack, I would say, slowly going higher, 11 or little bit higher, and then it goes stackable up to a few hundred kilowatt. Secondary side, DC started with 12 volt in a standard old, I would say, more standardized 48 volt now, but as the power is increasing day by day, we see a trend towards going it towards 400 volt also. We have some customers talking about 400 volt. Same like DC charger, this 400 DC, 400 uh, voltage category of battery voltage or 800, the same journey has started for AI server. So silicon carbide as a whole is mandatory, I would say, because you have to have a active PFC, power factor correction has to be properly done, and you have a DC-DC. So primary side of the DC-DC, silicon carbide is mandatory. Secondary side, either GaN or MOSFET, basically. The major why silicon carbide? First is, of course, the power density we need to achieve, which is not possible for silicon carbide. Efficiency needs to be achieved. So it's almost like a mandatory case for silicon carbide and GaN. You can ask the GaN. I mean, you can talk about a little bit why silicon carbide and GaN. Basically, we see both guys are penetrating this area. Silicon carbide bit more earlier in the market, and I would say more reliable and having multiple sources are getting a little bit more momentum, I would say. But GaN is also making progress. It's a really innovative solutions, topologies, and high switching frequency. So we say both guys will coexist in this, and having different topologies possible. Basically, it is 650 or 700 volt voltage category applications will drive this. I think, Alfred, you are muted.
Sorry, but yeah, it's always the trick, yeah, when you have to cough a little bit because my voice was like Paul's about a week ago. So I'm still recovering, but that's just a side thing. When I was at APEC, I saw really the battle for AI servers. So we really, if we have a look at the projections, how this market will develop, it's really mandatory to have low power. But my question is, where else do you see it really mandatory to save a lot of power and to increase the efficiency?
So other than AI server, which other
Yeah,
applications?
exactly.
Okay.
Yeah.
Basically, all the guys who are selling power, basically EV charger or board charger, because they're basically the guys selling the power. They are ready to save every penny because they are selling power. So off-board EV charger, one of the highest efficiency demanding application, I would say. Onboard charger, I would say it's the second. They are basically bothered more of compactness. I think these two, if you say only the efficiency, I would say these drives are, I mean, I would say number one or two, AI server and offboard EV charger, not the onboard one, as efficiency driven application first, as priority number one. Then the compactness and other things comes. As I think I already told my competitors, the basic advantage of silicon carbide is giving high efficiency at non-full or partial load. No? And most of the AI server also EV charger, you don't have a fixed load. There is not efficiency at rated load, rated power, rated condition, right? Most of the time, the application runs at partial load and certain jump of data or certain jump of load. And that's what I see silicon carbide really outperforms all the others in partial load.
Okay. So let me just have a short look. Something that was mentioned in the story is in which way SiC provides benefits when there are extreme thermal conditions. Maybe you can outline that a little bit more.
Yes. So I think we have a lot of supplier and different topologies, technologies, all are fair. The people are more concerned nowadays about reliability, the reliable operation. There are different technologies, even in silicon carbide, you have a trench and planners, no? Of course, you have E mode, D mode. But the reliability is the key parameter which differentiating all the other players. Now in reliability, we have few parameters. Of course, people want to go to higher temperature. Usually earlier, people maximum device temperature, they used to tell 100, 120 degree. I want to shut down, let my converter work around 70 degree to 90 degree and I shut down, right? Now they want to have the device temperature go a little bit higher, not 80% rate anymore. So we have seen still the devices are shutting down 150 or around this time. And then you have to really, so because they can really reduce the size of the heatsink or the cooling circuit, right? If you can drive the converter at high temperature. Usually the static parameters we have to really see, no? Usually the leakage parameters, IDSS, IGSS, you have to really see throughout the temperature how they behave, especially at high temperature, they should not be very hot. There's one more major parameter our customers are concerned. We call the threshold variation of our gate. This is one. So, the threshold voltage varies over the temperature, and you have to really know how much is the minimum to maximum over the temperature, because then you can have a proper gate drive system, not to have any shoot through or parasitic turn on incident, things like this. Another important parameter people ask for is the body diode degradation. Usually very important parameter when you're designing for the hard switch or the circuit with high deadband times, we say. So I would say these 4 or 5 parameters, it is sometimes documented in many data sets, but I think customer are looking for more data. No, I mean, not many manufacturers putting all the data openly in the data set. It's not sometimes not possible, but the designers really need to look into it, which parameter impacts their application. No, it's not about only static parameter. I told sometimes it is the dynamic test conditions. At what time you're shutting down, what is the E on and E off varies over the temperature, and the other important is RDS on variation. Very important parameter. How your conduction wall varies over the temperature directly relates to your RDS on. For example, Nexperia part, one of the best RDO stability we have, from 25 degree to 175 degree, we hardly have 40 to 50% variation in RDS on. This linear scale exactly give advantage when you're having higher conduction losses at higher temperature. You have a predictive loss and quite linear. This gives a lot of advantage in the conduction losses high temperature. So as I told, so reliability is the key topic, and we have to have really a good control over the methodology, no? Verification of the bare dies, and of course the packaging techniques and the reliability qualification is very important to differentiate in the market, and we're really focusing in this topic.
In the conclusion of the story that was published in the December issue, and it's the story we are talking about, you said the goal is to build a comprehensive static and dynamic performance data set. So how far did you get in that?
I think as a customer request, as I told, the data sheets doesn't carry all the information. No, we have to do a lot of other tests to have the reliability parameter in place, and we share with the customer as and when required. The article just gave a glimpse of what needs to be looked into it. No, now depending on the customer request, we share a lot of reliability data over the temperature variation, all these things. No, one to one. So as I told, the process are in place. Of course, we'll not deviate too much in a data sheet, but we'll try to give more and more information so that the customer feel confident using our devices.
Okay, thank you. Are there any more questions? Did anything come in? Then I think it's now time to go ahead and to say thank you very much to you, Pradip.
Thank you. Thank you. Have a nice day.
Thanks for participation.
Thank you.
And yeah, so we will come to the last story in our SiC session. And I see that Dr. Adam Barkley from Wolspeed is already there. Hi, Adam. Welcome. Welcome to Bodo's Power. And you will surely have some comments about your generation 4, which was already mentioned in the chat. You saw the question. Maybe we can start with that right away.
Yeah, great. Maybe let me introduce myself to your listeners. This is the first time I've been on this kind of a panel. So I'm Adam Barkley. I lead our die technology development business, but Wolfspeed, generally speaking, is a vertical organization. We sell bare wafers, epitaxy wafers, bare die products, discrete packaged MOSFETs and diodes, and multi-chip power modules as well. And so I appreciate the time to be here and speak on these. I'd love actually the opportunity to respond to a lot of these questions in the previous discussion because they do resonate with what our approach to our latest generation 4 MOSFET technology platform is. If that's okay, I'll just respond to a couple of the questions.
Yes, please go ahead.
Okay. Yeah. So first of all, I completely agree with Pradip on the increased customer awareness of and demand for silicon carbide in more than just datasheet room temperature RDS(on), which has been the historic kind of fighting ground between the companies. That approach to do more than just RDS(on) down and come up with a holistic ability to respond to many markets and end applications was the basis of our philosophy in this platform. So we are also seeing a desire to simplify circuit topologies at the higher voltage end of the spectrum. So this move from 3-level to 2-level converter topologies, particularly on renewable and solar, for all the reasons that Semikron Danfoss mentioned. And I just mentioned that we do have a 2.3 kV node available in power modules in our Gen 4 technology today. So if you're interested, please check out our website there. Look at the data sheet to understand all the benefits. I certainly agree with the low to no switching frequency applications and edge rates for motor drives, automotive traction inverters. And really the important characteristic there is efficiency as it relates to range and ruggedness as it relates to short circuit withstand time and cosmic ray fit rate. And so we've made some significant improvements there for a 2.3 microsecond short circuit withstand time and really big improvements to the light load, the things that drive light load efficiency and range for these low switching frequency applications. Probably the thing that I'm most proud about is for the AI power supplies, the data centers, the industrial power supplies, universal, uninterruptible power supplies, where we are trying to get the most energy extracted out of like fixed sources and claim it all that we can. And in many cases, we're processing power multiple times as it goes into an energy storage system, out of an energy storage system, and particularly data centers and AI power supplies that are stored in, pretty dense warehouses where we need to get the waste heat extracted also with the heating, ventilation, and air conditioning systems. So generally speaking, the more times that power gets processed, the more opportunity we have to lose energy, and the total cost of ownership goes up in moving that heat outside of a building, right? So for the high switching frequencies, we've made some significant improvements to the efficiency, the ease of use, and the robustness at high switching frequency as well, particularly the capacitance ratio between the gate to drain and the gate to source, which directly speaks to Pradip's correct assumption that people want to avoid parasitic self-turn on and shoot through. And so the more that we can do to enable ease of drop-in and extracting higher switching speeds out of silicon carbide, we think that will help to move those markets. Finally, on the reliability and performance, it's another vector that we pushed on. So in addition to those, shoot through immunity, short circuit withstand time without having to do crazy additional things with gate drivers, we are offering higher operating temperatures to customers and die packagers, module manufacturers that can take advantage of higher operating temperatures. It does place some more stress, and you got to get a lot of the die to package interfaces correct to be able to take advantage of that, but it is something that we offer in the trade-off space that our customers can use. I'd welcome any questions from the audience.
Yeah. There was no question directly coming from the audience, but when I first heard of the Generation 4 SiC technology, I was impressed. But do you think the market, or how do you think will the market accept it? Do you maybe have already a best practice or something like that you can talk about? A good example that shows the benefits from a system point of view?
We do. The lead adopter in this space for the 2.3 kV is actually an uninterruptible power supply company, where they are interested for all of those reasons, for light load efficiency, performance, ruggedness, and related to cosmic ray fit rate, uptime requirement, and total cost of ownership reduction. Generally speaking, we've gotten positive feedback from our lead, early sample customers in all of those spaces that I mentioned in the low to no switching frequency application. So one of our automotive traction end customers feels that they can sort of reduce the total silicon carbide content area by about 30%, moving from our Generation 3 to our Generation 4 MOSFET. So while they're achieving the same level of performance, it's an ultimate bill of materials cost reduction for them, which means we can sell more.
Okay, there was another question in the feed. What are the target applications for the Generation 4 applications? I think we could talk for hours, but maybe you can keep it short and take out the utmost or the most important applications.
Yeah, we've talked about them already. We designed for basically all applications to receive some level of improvement, particularly the low switching frequency things for light load efficiency improvement with the RDS-on reductions at low and high temperature. That's a big key market for us. Emerging markets like the AI power supplies, data centers, UPS, where we can really take advantage of the benefits of silicon carbide and higher switching frequency to reduce size and weight of magnetics, cabinet space, floor space in data centers, and still achieve similar or increased levels of reliability. These are the big ones that are important for us.
Okay, so I personally don't have any questions anymore because the story that you provided was so comprehensive and gave a very, very good insight into the technology. And a little scoop, a little announcement. In our next issue, in the May issue, we will also have an interview with your CTO, with Elif Balkas. And yeah, she will answer also some questions that we had. And I don't want to ask too many questions ahead of time, but I'm really excited to see how this technology will develop and will be adapted on the market.
Yeah, that's
So
great. We know we work very closely on our technology roadmap to ensure we stay competitive in the future as well. So I would encourage any of your listeners, if they're more interested to hear about some more details of our Gen 4 platform, do check out our website for both a technical white paper deep dive and available products today.
okay, thank you very much.
Thank
This is the
you.
last chance for questions before Bodo will take over. I think, Bodo, it's your turn.
It's
Thank you,
my
everybody.
turn. Thank you, gentlemen. It's coffee time. You have seen. I hope everybody of you have a cup of coffee nearby. We have a break, and soon we'll continue with Scan. Thank you so much, and be aware there are a lot of these fishes around in the world, and be aware of them and keep safe.